Since after this tutorial is lunch, I don't think I should wait. I should get started. There'll be lots of pauses throughout the session. So if you're still getting things downloaded and getting things set up, don't worry, you'll get a chance to catch up. If you need USB sticks with the data set, and we have a couple that have the notebook that I'm going to walk through, we have those as well. So just raise your hand. But I'll get started. Can everyone hear me in the back? Yeah? Good. All right. So this morning I want to cover a few different things. We'll do a brief introduction. Then we're going to jump in and do some data engineering and feature engineering. We'll do some modeling. We're going to spend some time talking about sentiment analysis and how useful it is and techniques for building sentiment analysis models. And then we'll talk through deploying those types of models as a service. So you guys are here at the Introduction to Machine Learning Applications tutorial. Hopefully that's where you're supposed to be, where you want to be. I'm going to pace things with pauses, so feel free to follow along. You don't have to. When I get to writing stuff on the notebook, it might go a little quickly so that I can help folks that are having trouble. But you should be able to follow along. And if you're getting stuck, please interrupt us. Raise your hand. We'll try and address questions and problems throughout the session. When I keep saying we, let me introduce the two of us that will be presenting. So I'm Rajat, and Brian is here from Dato. So we also have Alicia in the corner from Dato as well. So we're three folks that will be here throughout the session with you guys. So you can see the notebook is still, the notebook I didn't finish until last night, so that's why I didn't put it on the USB keys. But you should be able to get to it from that link. So I'd love to know a little bit about the room. So let's start there. So how many of you have heard of Dato? All right. Is it because of all the signage here? Be honest with me. Yeah? No. You knew about us beforehand. Good. All right. GraphLab? Any folks that didn't know about Dato knew about GraphLab? All right. We're the same group of people, same project, and now we're a company. So about you guys, how many folks consider themselves data scientists? All right. Data architects? All right. Data engineers? All right. Pythonistas? Oh, come on, we're at the PyData conference. No? We're not all Pythonistas? OK. And what else? I only saw half the hands go up. So what do what's that?
Shy. They're shy.
No, they're shy. I was like, that's not a job I know about. OK. Well, I'd love to find out what you guys work on, if it's not any of these things. So I should give you a brief intro about Dato, just so you understand what we do as a company. I thought the best way to do that is to show you a few demos. I'm not going to go through a big pitch of any kind, but I thought it would be good to give you a brief introduction. So Dato is a machine learning platform, and our focus is to help developers and data scientists build applications that use machine learning. So here's an example application. This is a product recommender. Let's see, can you guys, you probably can't read that. Let's try that. Is that better? And so when I select a product, like a dumb movie, like Dumb and Dumber, I'm recommended other dumb movies, like Happy Gilmore, Ace Ventura, Liar Liar, Cable Guy, Tommy Boy, Black Sheep, and Big Daddy. How many of you have seen Dumb and Dumber? The original Dumb and Dumber from over 20 years ago. Yeah. So do you guys think these are decent recommendations for physical comedies from the mid-90s? I have to admit that I've seen almost all of these, at least all the comedies. I've never seen the new Nightmare movie, but I don't know if that counts or not. So what's that? Yeah, Rocky V. Have you seen Rocky V? I think it counts as a physical comedy in my book. Because in Rocky V, he fights in front of a public city bus on the street against Tommy the Gun or something anyway, it's like a protege that goes against him, if I remember correctly. So this is a fun application, right? Product recommenders, we use these all the time. So with Dato, you can easily train and deploy these types of applications, build this type of application. So for this demonstration, we built a recommender model trained on the Amazon review data set and deployed this as a service to AWS. And that's what this application's using. So fun example, I could take a live book, movie, or music album title. It just can't be too current. It's got to be from 2013 and before. Say it again? Catch-22. Oh, I didn't know there was a VHS version from 1970. That's cool. So Catch-22 were recommended Slaughterhouse-5, A Clockwork Orange, Sun Also Rises, Invisible Man, The Great Gatsby, Cat's Cradle, 1984, Breakfast of Champions, Brave New World, and Heart of Darkness. What do you think as recommendations? I could say that, like, if you went to high school in the U.S. like I did, you've probably read half of these throughout your schooling. So probably not too bad. So there we go. That's an example. Let's do a very different type of application. So let's look at dresses. So in this application, maybe I should zoom in again so you guys can see this a little bit better. So I need to buy my wife a dress. And so how do I go about doing this? Today I might go to a website and type in dress and then see a bunch of dresses. Unfortunately, I don't really know anything about dresses. And so when I hover over them, I get these text descriptions. And here I'm seeing the most important words or significant words of that text description. I still don't understand any of them, though. I don't know the different cuts for a dress. I don't know what glimpsed means. I don't know what any of these things are. But I do know that my wife wants a cocktail dress. So maybe I can filter the dresses, and now I can see that these are all cocktail dresses. But again, I still don't know how do you describe this dress versus this dress. But you know, I know that my wife would like something like this. So when I click on it, I'm immediately shown other dresses that look similar. And if I shrunk this a little bit, you guys would see that side by side. And so how did we build this? So again, this is a simple application using Dato. What we did is we took a deep learning model that was trained on one data set, the ImageNet research data set, and we used that model to extract features from all of these images. And then using those extracted features, we trained a simpler model, a nearest neighbors model. And now, when I select an image, I'm shown the most similar images to that image. So I'm actually seeing there's no metadata, none of that text descriptions applied here. It's just the images themselves. So that's how we built this application. And this can help, obviously, for helping me figure out which cocktail dress my wife would like, but also in applications where similar for images is important. So this is a second application. Again, we built this using the products that Dato offers. And we have this deployed in AWS. And the last one I'll show you is one that's very relevant to today's tutorial. So by the end of the tutorial, you should be able to build the building blocks for this demo. I can't say you'll be able to build the UI, because I can't build this UI, but we will at least do the data science and machine learning part. So this demo is about sentiment analysis using text from Yelp reviews, or Yelp metadata. So I'm in San Francisco. I'm in San Francisco all the time, though Dato is based in Seattle. I spend a lot of time in San Francisco. One of the things I always want to do when I'm in San Francisco is get a good burrito. So what does good mean to me? It means I want it to be an authentic burrito. When I go to Yelp, like all of us have done, I'm sure several times, and you go to look for food that might give you a burrito, you get thousands of reviews. How do you know which reviews are actually helpful in you don't want to read 1,000 reviews. You want to read the 10 reviews that talk about how authentic the burritos are. And that's pretty hard to do today. But if I search for burrito, authentic, and dirty, because I don't necessarily want to eat at a dirty place, I get back a score for each of those keywords from the restaurant. And so now, let's pick one of these places. So let's pick, I think this is the one that I've been to before. And so now when I click on that, I now see the individual score for each of these 3 words from Taqueria Guadalajara. And then when I click on authentic, what I see now are the most positive and negative sentences from all of the reviews of this restaurant that refer to authentic. Does that make sense? So this is sometimes called aspect mining, where you're not looking for overall sentiment of the entire review. Did you like the restaurant or not? Instead, you're looking for a specific aspect of the review, and then you want to predict the sentiment of that aspect. So I don't care about the entire cell phone review. I only care about the battery life of the cell phone. So I want to get the sentiment of the battery life component or sentence of the review. Does that make sense? And this is what we're going to get to by the end of today's tutorial, is doing exactly this. So what you can see for this place is for Taqueria Guadalajara, the most positive sentences are burritos. Surprisingly, all I remember from the night is that the burritos taste authentic, not like these other places. The second one of the best authentic Mexican food I have ever had. And they talk about all these other places. Now let's see what the negative ones are. The first one, authentic Mexican food, fairly priced but not very clean. So even the negative sentiment sentences that refer to authentic still speak positively of the authenticity of the food. So that's kind of where we're going. But I wanted to give you this quick overview of the types of applications you can build using Dato. Let's get back to a couple more slides. And just in general, we're going to do a few slides, then we'll pause for a hands-on session, probably 15 minutes or so. I'll poll the room to make sure folks are mostly caught up, and then we'll move on to the next section. So, of course, this isn't the only time you can hear from folks at Dato. Later this afternoon, Brian's going to be talking about density-based clustering in Python, where some of his recent research, along with some of the work of other projects in Python. Really cool. I'm hoping to get to attend. And then tomorrow, Sean is going to talk through thinking about machine learning models in production. I'm going to touch on it briefly today, but there's going to be a lot more depth in Sean's talk tomorrow. So check us out there. So what do I mean by a machine learning application? What does it mean to, how is this different than data science today? So if you look at data science today, it might look like this. You start with some data. Could be messy from all these different places. You've got to clean it up, extract features from it. Then you're going to split the data set, right? So far, so good, into a training set and a validation set. Then you're going to train a model, and you're going to evaluate how well that model's doing based on your validation set. And what's the next thing? You go back to the beginning and start over again. And this is sort of the iterative loop of data science. Well, this is subtly different than what I mean by a machine learning application. Though it has a lot of common elements to it, this isn't the end of the process. In fact, this is just the beginning of it. So let's walk through the entire process of building an application that uses machine learning. So you start with conducting some experiments, and you'll have to excuse my DigitalOcean logo. But you always start with data. This is similar to the data science process. You start by exploring it, and you start modeling. But you do this in this iterative loop. This is the same as the data science process. But at this point, your goal here is to prototype. You're trying to see, is there signal in my data? Is there something worth exploring? So depending on what your application is or what your goal is, if you're looking to predict if a customer will leave you, if you're looking to predict churn, you're trying to see, do I have the right features? Do I have the right data? Do I have the right model to actually make this sort of prediction? So this is this iterative prototyping step. But your goal from this prototyping is different when you're trying to build an application. Your goal is to get to a pipeline. And this is where we're going to spend today's session, is talking through the parts of going from that prototype through to a pipeline. So the first thing you need to do is take your unstructured data and ingest it so that it's in a structured form. And then you're transforming your data. And this is typically the feature engineering or feature selection step. meaning how do I change my data and transform it, and I'll drill in on this a little bit more so that a model can interpret it. Your next step is to model, train models, and evaluate those models, typically using offline evaluation criteria. And finally, to deploy those models. And when you're thinking of deploying a model, there's kind of the old school way of doing it, which is taking a model and generating predictions in a batch way and then recording those predictions somewhere. That's how things have always been done. But today, more and more people are looking to take that model and deploy it as a service so that you can use it for real-time predictions and make it easy to update the model with, and improve on that model. So that's what we're going to zoom in on. So far so good, right? These 4 steps: ingestion, transformation, modeling, and deployment. These are the 4 components of a machine learning application. But if you think about this as building that first application, you're not quite done yet though. Because imagine you got that first application built and now you're looking to deploy it. So you want to deploy those models as real-time services or as a REST API, so as a set of services. So now you can easily integrate this model into the rest of your application. Chances are your application is comfortable making web service calls. So this integrating your model is as easy as integrating another web service. Once you've deployed as a service, you want to be able to get feedback from the model, use that feedback to update the pipeline or update the model. All the while, you're not sitting around idle. You're working on the next version of this model or the next version of the pipeline. And once you have multiple pipelines deployed, you want to be able to conduct online experiments. So this is A/B testing or multi-arm bandits. So this is the complete life cycle of an ML application. Does this make sense? Everybody okay with this? We're going to zoom in on these 4 components though. These are the 4 components that we're going to talk about in today's session. Ingesting data, transforming that data or feature engineering and feature selection, modeling, including some bits on evaluation, and then finally deployment. Okay. Any questions? No? Everybody's so quiet. Okay, go ahead. USB sticks. Yes, we do have them. So the notebook is at that link. The data set is on the USB sticks. Anyone else need USB sticks? A few more. Okay. So maybe we can just, Brian, if you want to walk around and, all right, sweet. Is that a question or are you looking for, go ahead.
Python 2 or 3 for this tutorial?
Python 2. We're working on Python 3. It'll give us a few more months. We'll have Python 3 support. It's something we're actively working on. It's a great question. Any other questions, guys? All right, we're going to jump right in. But please stop with questions, interrupt me. Don't feel like you have to listen to me this whole time. I want to hear from you too. So the application that we're going to work on is using Yelp review data. So it's about restaurants, very similar to the demo that I showed you for sentiment analysis. So it's going to take me a while to try and read these, but the first thing we're going to try and do is predict if a review is funny or not. And so the thing on the left, Rosie, Dakota, and I love Chaparral Dog Park. I don't know how to say that. It's very convenient and surrounded by lots of paths, a desert somethingscape, baseball fields, ballparks, and a lake with ducks. The Scottsdale Park and Rec Department does a great, wonderful job keeping the park clean and shaded. So does this seem funny to you guys? You're right, it is not funny. It's very informative, but not very funny. Whereas the one on the right, the oldish man who owns the store is as sweet as can be, perhaps sweeter than the cookies or ice cream. Here's the lowdown. Giant ice cream cookie sandwiches for super cheap. So is this one funny? I mean, it's funnier, right? So if we don't think of it as early in the morning, we may actually think this is funny. With a couple drinks in us, we'd probably laugh when we read this. So this is what we're going to try and do, is predict whether a review is funny or not looking at its text. So this is we're going to go through the same application. It's one notebook, but we're going to go in pieces. We're going to go through these 4 components, ingestion and transformation. We're going to do that first. Then we'll do some modeling. Then we're going to talk about sentiment analysis, and then we'll deploy. So that's the outline for today. So let's think about data cleaning or that first step of ingestion. It's really important that you know your tool. This is actually, it makes a huge difference because when you're working with messy data, like most data sets are, if you don't know your tools, you'll spend a lot of time just getting some basic operations done. This is very similar to your favorite coding environment, your favorite IDE. If you know some shortcuts, it can go you can be significantly more productive. The same is true when you're cleaning data. So you have lots of formats. Even a format that seems as well understood as CSV is, how do I say it, can leave you with some surprises. You can't read that, but on the left is Pandas read CSV. So kind of the workhorse in Pandas for reading text formats, and you can see how many parameters there are. So knowing the parameters can really help, because you can probably not spend time actually trying to write little sed scripts or shell scripts to make your data change its shape so that Pandas can read it. Instead, there's a way to get Pandas to read it as is. And on the right, you see the S-frame read CSV, which is another open source package. It's one that Dato offers for out-of-core tabular data. So again, lots of parameters. A specific thing to pay attention to is missing values. And this is really common when you're looking at data sets. Missing values can have lots of different interpretations, so it's important that you think about this when ingesting data. A lot of time spent cleaning data is just dealing with missing values. And finally, use some visualization tools. If you guys attended the Matplotlib session earlier today in this room, Matplotlib is a great visualization package. It's has lots and lots of options. But your goal here is to use some statistics to better understand what your data is like. How much cleaning do you have to do? That's an important thing to think about when you're getting started with the project. If your data needs a lot of cleaning, then you may want to think about, okay, what's the step prior to getting this data? Can I change that step? Whether that's an ingestion pipeline or the way the data is organized so that my data cleaning becomes easier. Maybe it's just as easy as saying, hey, you know, I don't need this as a CSV. The raw data is in JSON. I'll just ingest it that way. Or this data is coming from a database. I can just connect to that database directly and run queries against that database directly. So think about that sort of stuff in the data cleaning part. For today's tutorial, the data set's pretty clean. I tried to not, it's the raw Yelp review data set. So it has a couple warts in it, but chances are your real data is messier. It probably needs more cleaning. So feature engineering, we're now on to step 2. This is transformation. And really these often go hand in hand, because the intent at the end of this step is to have the data in a format or have the data ready for the model. And so at a high level, your goal with feature engineering and feature selection is to get your data set prepared so that the model can understand it. So a simple example is continuous variables into categorical. So zip code is a great example. Zip code's a number. It's probably an integer in your table or in your data structure. But having a greater zip code, like 10007, is not actually greater than 10006. So that's a really simple thing, but you don't want the model to interpret a zip code as anything other than a label. And so you want to make sure that you're interpreting columns as integers only if you actually expect the model to interpret and to learn that that's a continuous variable where a bigger number actually means something. Otherwise, you want it to simply be a categorical variable or a label. So day of the month is another one where that's an important thing, or the year, really common examples. So another pretty standard feature engineering technique is to create aggregates. And so you often don't need the exact number. An example of this could be your age, where your age is actually a continuous variable. So being 50 means something other than being 30. But you may not actually care about how many 50-year-olds versus 51 versus 52. You may want to quantize or bucketize. So 18 to 34-year-olds, 35 to 50-year-olds, like that. That's a really common feature engineering technique because, again, the specific number isn't important, but a range or a bucket is more important. The same for text. So you might have a full document. Maybe you only care at the sentence level. Or maybe you actually only care to look at n-grams, so bigrams, which are two words that are next to each other in a sentence, or 3 words that are next to each other in a document. And so for a lot of different techniques, it's this sort of manipulation that's what, this sort of transformation is what you're doing for feature engineering. Now, we talked about missing values. What do you do when you have them? So oftentimes you want to impute missing values, or you want to essentially fill in missing values using something else. So a standard is to use an aggregate. So I will take the average value in this data set and fill that in for all of the values that are missing. Not sure if that works in every problem, but that's a pretty standard way of doing things, where you take an aggregate, or you say, okay, what's the mean? What's one standard deviation lower? I'll make all my missing values that. Or a more complex example would be to use a separate machine learning model to predict the missing value. So this is also really common as you're building up these model pipelines, that if you have missing values and missing values there's no way around them, you may be able to train a model to predict the missing value and then use that to fill in your missing values. And finally, and we're going to do a tiny bit of this, I call this use data encodings as new features. So you might have lots of data. So the idea of using an encoding, can you guys can see that, okay, let me try and give an example. So if you're thinking of user profiles for Facebook, for example, or for a social network, there are lots and lots of fields, lots of metadata about each user. Now, do you want to think of each of those features independently, or as is it actually important that each of those features be considered by the model? Maybe not. You may be able to get away with simply saying, I want a hash for all of these features, and I only want this to be in, I only want to use 15 bits to represent this hash. So that's a way of reducing the dimensionality of the problem, taking away some of those features, but still getting a representative hash for those feature values. So that would be feature hashing. So that's what I mean by encoding your data as another feature. And so this way you can avoid using all the specific values for something, for all the specific features, and instead use an encoding. And what we'll use today is one-hot encoding, which is a technique for, the way we're using it is to reduce dimensionality, where we'll say, given this entire corpus, or the entire vocabulary of these text reviews, I only want the top 5,000 words. So that means there might be 20,000 words, vocabulary of 20,000 words used across the corpus of reviews, but I only want the 5,000 words that are used most commonly. That's a really simple way of reducing the dimensionality so that the model can learn more easily. Does this make sense in terms of what we're doing with feature engineering and feature selection? Okay. So now I'm gonna switch over and jump to using the notebook that, if you haven't gotten yet, you can still get from this link. And we'll start by doing some operations in using the S-frame. Now, you can pip install the S-frame. It's a Python package. It's open sourced. It's also part of GraphLab Create. And since we'll use GraphLab Create for later in the tutorial, my notebook doesn't use S-frame directly. It uses it as part of GraphLab Create. And then we'll use GraphLab Canvas, which is a data visualization tool. It's part of GraphLab Create to give you a sense of the data. Does this sound good? So, all right, we're going to switch over to a notebook. And can you guys read that? Does that seem right? I'm going to go full screen and then get rid of these headers. So full screen. So how many of you are familiar with IPython Notebook or Jupyter Notebook? Almost everybody? OK, good. So then I won't really cover this. So we're going to use, since we're using sframe to do our ingestion, sframe is part of GraphLab Create. I'll just import GraphLab to get started. You guys can all read this, right? Is this OK? OK. I say this, but it's actually hard for me to read this. Let me see if I can do. The angle of the laptop is not awesome. Nope. All right, we're just going to do this. Don't mind me staring down at my, oh, maybe I'll do that. I'll look at that. OK, better. OK, step one is loading the data. So I have this, so you can also see where this data set came from. So you can download it as a zip file, or you can grab it off the USB key if you haven't gotten it already. And I have this as a JSON file written on my file system. So I'm going to call read CSV, which actually can read JSON and can read anything else. And I can change this to JSON. But we'll read CSV. And there's no header row in this. So we'll run this. Oh, come on, scroll. So this file has 229,000 rows, and we parsed it in 2 seconds. Let's look at a row. So a specific row from our from the sframe. So the sframe is a tabular data structure. So one of the rows from that table. What you can see is this is one big JSON document. Yes?
Why are you not using pandas?
I'm not using pandas for 2 reasons. The sframes I could use pandas. I'm less familiar with the pandas API. I'm more familiar with the sframe API.
Pretty similar?
They're very similar, yeah. Pandas were very, so pandas was inspired by the R data frame, and the sframe is inspired by both the pandas and the R data frame. The biggest distinction is the sframe is an out-of-core data structure. So pandas requires your data to fit into RAM, whereas the sframe does not. So you can work on larger data sets. So on this laptop, we could work on a terabyte of data because even though I only have 16 gigs of RAM on the laptop, because it's an out-of-core data structure. And it's the data structure that GraphLab Create relies on for its models. So when we get to doing sentiment analysis models in a little bit, then we need to be using an sframe. You can obviously convert a pandas data frame into an sframe and vice versa, but might as well use one system. Does that make sense? It's a great question. Honestly, I wish I knew pandas better, because pandas does have more options in the sframe today for ingestion. But for this problem, we're OK. We see that this is a JSON document. So this JSON document has 1 column. And if we look at, we can look at the column types. And you see that there's just 1 column, and it's of type dictionary. So GraphLab, or the sframe, was able to ingest the JSON file and realize that each row was a single JSON document, which in Python is encoded as a dictionary. So far, so good, right? So let's start. Let's actually get this into something usable. So this is, it's not horribly dirty, but this isn't how we want to model. And remember, our first goal is to predict funny or not. That's our first goal, is given the text, can we predict if this, this review is funny? So each review is a JSON document. Let's unpack it. So with this command, we're basically saying, take the column that's named x1, and we want to unpack it with no prefix. So let me show you what this looks like now. So it's a little hard to read, but you can see that we've unpacked. So now business ID, date, review ID. Scroll over and scroll back. Stars, text, type. And there's a few more columns, actually. But you see this is exactly what we had before. Business ID, date, review ID. But these were headers, or these were nested JSON inside the outer JSON document. So we've just peeled back or exploded that outer layer JSON. So now we have these columns, and we're halfway there. I lost my cursor. OK. Let's see. So the next thing we notice is that the votes. So Yelp reviews are great because people have actually, they vote on the reviews. But those are trapped inside a nested JSON document inside this. So let's unpack it one more time. And then let's look at what our data structure looks like now, what our table looks like. So you see, so far it looks the same. But let me scroll down. And now you can see that the 3 types of votes, cool, funny, and useful, are all exploded. So now we have one table. So now our data is kind of ready. There's still some more things we want to do, but this is actually closer to how we want the data to be represented because we're going to take advantage of this funny column. So if someone's voted a review as funny, then that's what our model should learn, right? It should predict that a review is funny using this label. Go ahead, is there a question?
So on data prep, you can also query using SQL-like language.
Yep.
So could you have done the same thing here? Okay, if the score is beyond this, then I'll display this data.
That is right. In fact, we're going to do that in 2 steps. We're going to do some logical filtering, some group bys, some joins. We're not going to do joins and group bys today, but we'll do some filtering as part of our feature engineering step. OK. So GraphLab Canvas is our visualization and data exploration tool. I could do all of these operations from the S-frame itself. So getting aggregates, getting stats, but it's sometimes easier, and maybe I should zoom out on this screen, to just look at the data using Canvas. So what's happened in the background is we've done a one-pass sketch summary over each column. What this means is using some pretty clever sketching techniques, we've, in one pass, have been able to provide approximate statistics. So this went really quickly, 230,000 rows. But if you have 10 million rows, this goes, it's still at interactive speeds. And the advantage here is when you're in this step, when you're ingesting and cleaning your data, you often don't care about the exact mean of a numeric value, the average. But an approximate average is good enough. Or looking at a standard distribution or a box and whiskers plot of something, of a numeric field, a numeric feature or a numeric column, you want to get a sense of the distribution. The exact distribution is less important. An approximate is good enough. So what we see here is when we look at stars, we see that there's 5 unique values. This makes sense, 1 to 5. So the min is 1, the max is 5, the median is 4, and the mean is 3.7. So what does this tell us? If we click on it, we should see a histogram here. This tells us that most people give a review 3 or better. And so that's an important thing. Most people don't write, more people write positive reviews than people write negative reviews. And so that's useful to us. Or actually, if you look at, that was looking at it numerically. If we look at it categorically, this is what you want to see, that the most common review is 4 stars, almost 35%, followed by 5 stars at 33%. So at 67%, over 2/3 of the reviews are 4 or 5 stars. So that's important to know. OK. So this is the type of thing you can do with Canvas. It's why it's useful. You can also just scroll through the data, which is also useful. 220,000 rows isn't a lot. You could do this in Excel. You could use Vim and probably poke around a bit and just be fine. But when you have 10 million rows, this can actually prove to be pretty useful. And the paging in and out is because of the S-frame. OK. And some basic plots, which I won't cover but in this tutorial, but is also useful in this exploration phase. Let's see if we can do something like user ID and stars. I don't know if I want a bar chart. Maybe I do. So yeah, these are all different user IDs. I can scroll through them. Stars is not what oh, count, yes. So this tells you this user had 498 reviews. And that's amazing. So you can see this, that there's a distribution. The number of users that write reviews is also varies quite a bit. OK, so that's S-frame. That's Canvas. Let's get back to our notebook. The full screen thing makes this. Here we go. This is where we were. Okay, so we got a sense of our data. We see that there's definitely more positive reviews, 4- and 5-star reviews than anything else. But what we want to do is get to predicting funny. So let's filter out reviews that have no votes. So first, let's create a new feature called total votes, which is the sum of the number of votes given saying a review is funny, plus cool, plus useful. So this is the total number of votes. So it's kind of like how many people said anything, voted in any way about a review. So let's do that. And we assign this to a new column in our table. So we've created a new feature now. Now, let's filter out, and this is what you were mentioning before, let's filter out all the rows that have no votes. So in other words, we don't want to learn on something that maybe no one's ever seen. So we want to take away all of that data. So that's a logical filter. So I'm saying give me the reviews table, give me all the reviews where total votes are greater than 0. So we'll do that. And then finally, well, actually here, let's pause for a second and show you what reviews looks like now. So it has the same shape. The main difference you'll see is that there's less data now. So we used to have 229,000 rows. Let's, the S-frame is lazily evaluated, so it only does what it needs to. So I need to actually get the length of this to get a sense of how many rows we have now. So now our table has 147,000 rows. So we just took out 80,000 reviews because maybe no one's ever seen them. No one's voted on them in any way. Does this make sense? This is a form of feature selection where I'm going to remove some data from my data set because I don't want to consider it when training. And finally, let's binarize funny. So right now, funny represents the number of votes, the number of, for a given review, the number of times that review has been voted funny. Well, I'm just going to say if that number is greater than 0, I want it to be 1. In other words, I'm saying true or false. You're either funny or not. And so if you have a vote, if that review has ever been voted funny, whether it's once or 10 times, just consider it funny. Does this make sense? Good. We're going to do that. And now we're going to just cut all the other stuff out of our table. So we're only going to select these 2 columns, the text column and the funny column. So you can see what my table looks like now. I just have text, and I have funny, where funny is either 0 or 1. Now I have the data I want to train my model. Go ahead.
Yeah, so I have a quick question in that one. For
Sure.
example, if particular text has 100 or maybe 1,000 words, but only one of them is funny, right? And then we are still considering that to be funny.
It's a good question.
Maybe that's not funny, right? Because out of 1,000, it's just getting 1 word.
So the question was, what if the review has 1,000 words in it, and only one of them is actually what makes the review funny, or one of the words is considered funny? How are we accounting for that? So remember, our goal here was to predict whether the entire review is funny or not. Whether or not so if it's 1,000 words, that's fine. If that 1,000 words, at the end of it, your sentiment is this is a funny review.
No, actually my question was, for example, there are 1,000 votes,
Mm-hmm.
and 999 people didn't vote that review is funny.
Mm-hmm.
Only one person voted as funny.
Right. Okay. So that's a different question. So you're saying, how many people saw this review, and of the people that saw the review, maybe 1,000 people saw it, only one person voted the review as funny. Right. We don't know how many people saw these reviews. Our only indication of interaction is based on the votes of useful, funny, or what was the third one? Cool. And so we don't actually know seen, whether these reviews have been seen. So our closest interpretation of that is if you have no votes of any kind, then maybe you've never been seen as a review. So we actually aren't considering the case of, well, only one person thought this was funny. And for our predictor, I think this is okay.
It's not weighted, basically.
It's not weighted, that's correct. We're not weighting, we're saying either you're funny or not, and we're only saying you're funny if anyone ever thought you were funny, ever. There was another question? No?
In general, how do you deal with the data sparse? Say you have a really sparse data set.
Good question. So the question was, how do you deal with really sparse data? A few different, there's lots of options here. One is you want to adjust class weights. So another standard is you want to balance. So if you only have 1,000 labeled samples and you have 10,000 unlabeled, you want to sample from the unlabeled so that you have a balanced set of data. So those are two really common techniques. Also, your data structures themselves should be good with sparse data. So you should be able to represent. You should leverage sparse data structures to represent sparse data. Otherwise, it's much less efficient. That's a great question. And any other questions? Is everybody following along? Am I going too slowly? Should I speed up? No? This is good? OK. I'm happy to speed up. But I probably will be less coherent. OK. So now we've got the raw text and a binarized version of if a review is funny or not. But how do we interpret that text? So let's do a couple things to give ourselves a better representation of each review. In fact, let's break the text into a bag of words representation. Bag of words or a frequency count. So instead, we want to see for each word in a given, so we want to see, given a review, we want to see how many times each word was used in that review. So this is a frequency count for the words inside a review. So here we'll use a text analytics tool, or toolkit in GraphLab Create, and we'll just pull out, we'll do count words. You could also do this in scikit-learn with count vectorizer. And I even tried to do this. This morning I was thinking I should have both. I should have both with, oh no, where is it? I had another notebook which is not here. Oh, here it is, logistic regression with scikit-learn. But I didn't get far enough along. But you can do the same thing using the count vectorizer function in scikit-learn. I already have this open. Why are you opening it again? Huh, weird. OK. We'll open this again. OK. So we're going to do this. We wrote this as a little Python function because we're going to use it more than once. We need this, and this is looking a little bit ahead. But if you're thinking about how do I create a pipeline, you want to think about the goal being the application you're creating. The goal is, this is amazing. I'm like selecting text, and I'm not looking to. Oh well. The goal is, given some text, I want to predict, like given the text of a new review, I want to predict if that review is funny or not. So all the operations that you need to do on the text itself will need to be repeated. You'll want to do this at prediction time. So it makes sense to write these operations as functions so that you can easily sort of do the pipeline of those steps, those pre-processing steps prior to getting a prediction from the model. Does this make sense? So let's run this. Wow. OK, let's get rid of that. Let's get rid of that. OK. So I talked about one-hot encoding before. This is what it looks like if you're using the one-hot encoding transformer in GraphLab Create. There's an equivalent in scikit-learn. And so the goal here is, given this, so let's look at the review data before we do this. So we just define the function. Let's why? Let's try reloading. My browser is not behaving the way I expect. I've lost all my shortcuts in IPython Notebook, which I am kind of useless without. OK. Should still be running. Let's make sure I have shortcuts. I don't. All right, we'll keep going without shortcuts, but I'm so much slower with IPython Notebook if I don't have keyboard shortcuts. All right. Okay, so let's insert a cell below this. And let's run this function on our review data set. Oh, maybe my keyboard has stopped working. That's amazing. Wow, OK. Well, let's run this cell, and then I'll give you guys a few minutes to work on this. I just want to see my output while I figure out what happened to my system. All right, I'll explain this, and then I'll debug my system while you guys can spend a few minutes making sure that you're at this point before we move on to the modeling step. But the key thing I'm doing here, and this is where this max categories comes in, is all the reviews, the 147,000 that we have left, they probably use a pretty big vocabulary, meaning there could easily be 10,000 or 100,000 words in this vocabulary. Maybe not 100,000, maybe 50,000. But I actually don't want to try and use all of them. So I only want to keep the top 5,000 words. And that's what my one-hot encoding, what the one-hot encoder feature engineering transformer enables me to do. And so this is a stateful transformer, like most of the feature engineering transformers. So in a way, it feels like a model. So you want to fit, and then again, you want to be able to transform, because you'll have to do this at prediction time. And that's why this is an important thing. So remember that you're taking a raw document, a raw review, and you want to predict whether it's funny or not. But you'll only want to count the words in that review that are in the top 5,000 from your training set. So that's why it's stateful. So we ran that, and now we're ready to train. And I really want to show you what this looks like, but I've lost my keyboard. And so I'm going to debug this. So give me a second to do this. You guys should definitely follow along. Make sure you're at this point, so then we can switch back to slides, and I'll talk through modeling, the model that we'll train, and then we'll come back and keep working on this. So give me just a second. So what do you do when you have Windows and something doesn't work? You turn it off and on again.
Buy a Mac.
You buy a Mac, yes. But then how do you test whether your company's product runs on Windows?
Those aren't users you want to support.
Those aren't users you want to support. That's funny, yeah. We said the same thing about 32-bit users. That, yeah, who has a 32-bit computer these days? Turns out lots of people have 32-bit computers still. Lots of company settings still have 32-bit images. So that was a lesson we learned. We still don't work on 32-bit machines.
Where does your system typically runs, on a server or a cluster? Or?
Yeah, it's a good question. The question was, where does our stuff run? So it always starts from your laptop, because that's where you're starting with all the prototyping. So from your laptop to a server to a cluster.
Small data sets.
So remember, since it's out of core, you're not limited by RAM. So you can work on much, much larger data sets on your laptop. So yeah, terabytes of data on your RAM, on your laptop, which typically actually lets you cover a lot of the data that you're using. All right, we'll start by launching. I've got a keyboard again, which is a good sign. Let's. I don't want to restore pages. Come on. Python notebook. And demos. Ha ha ha, I have a keyboard again. Yay. All right. Let's catch up. Okay, what was this guy? Amazing. Okay. Save. Okay, so it's 11:35. Is everybody that wants to be caught up to this point at this point? You don't have to be. You can just passively follow along. But if you want to be caught up and go hands-on, then I want to make sure you get a chance to catch up. If you're still having trouble or you're stuck on something, raise your hand and Brian can swing by and chat with you. Brian's back there to the side. So I want to talk about modeling next. So far, where are we in this process? Well, we ingested some data, this JSON review data. We transformed it. So now we've gotten the text. And you know what? I should show you this. This is one thing I wanted to show you that before my laptop went haywire. Let me show you what the data looks like now, after we completed this encoding step. So if we look at train, so this is our review table after we ran this select features function to get a bag of words representation. So now text is the same review, but now with a frequency count on each word. So you can see that this first review said better, looks, go, each with only a count of 1. And then let's look at encoded, which is after we've done the one-hot encoding, what things look like then. So what you can see here is that I have a numeric value now with a count of 1 for these top 5,000 words. So that's the encoding that I'll learn. Okay, let me get rid of this header, but I won't go into full screen because I don't like full screen. It's more confusing for me. All right, so let's get back to modeling now. Let's talk about the actual machine learning model, the model that we want to train. So modeling is that core component of anything you're doing with machine learning. And a very simple way of thinking about it is a model is a simplified view of your data. So you're thinking of a simplified representation or a way you can consider your data in a more simplified form than actually using all of your data. And so I like this quote, all models are wrong, but some are useful. So that's a good guiding principle when you're thinking about modeling. So I only want to talk through, I'll talk through one model, and I'll do this pictorially. There's lots of resources available that can do a better job than I can to go through logistic regression. But this is the model that we'll use. It's a linear classifier, meaning the way that I think of this is that you're fitting a line to a set of data points. So if you have a bunch of data points, you're finding the mathematical function that most closely reaches those data points. That's the idea of a linear model. And when I say most closely, you're minimizing the error that you have from the data points. And you don't want, and so that's the idea, that we're fitting a line to our data. So let's look at it in the context of funny and not funny, whether based on the number of stars and the number of votes for useful for a review. So what does a linear model learn? What is it learning? Well, it learns a weight for each of these features. So stars is a feature, useful is a feature, and when you give both of these features to the model, it's going to learn a weight So mathematically, if you're thinking of how do you define a line, y equals mx plus b, right? B is your intercept, m is your coefficient, and x is the variable. Well, this is the exact same thing, right? Except you're looking at a polynomial. So many coefficients, one per feature. And Brian, correct me if I'm getting this wrong, by the way. So far, so good? Good. So what are we learning? What the model learns is the weights for each feature. Meaning, and so the idea here is we're trying to minimize, so we have a label. We know whether something should be considered funny or not. So we want, given that data, we want to fit a line that is as close to the correctly predicting funny while incorporating all of the other features. So the idea that this model could learn that stars has a -3 weight. This feature has a -3 weight, and useful has a +1 weight. So now, how are these weights? This is what the trained model actually has, or it has learned these weights for each feature. So what is this? How do you use this at prediction time? So pictorially, you always start with your constant. That's going to stay the same, and you multiply the weight by the value in the data. This is exactly the mx plus b, right? So if you know m is the weight, x is the value. So we'll do that. We do the same for useful. And we see that this is 2, since it's greater than 0, right? Logistic regression, 0 to 1. Since it's greater than 0, we are now funny. That we're going to predict this review is funny. Let's do the inverse case. If you take 5, well, I can't point at this. This isn't useful. You guys can't see this. If we take 5 and 2 and do the exact same thing, we now see we're negative. We're at -13. That's less than 0. This review is not funny. So does this give you an intuition of what logistic regression is doing and how we apply it? Good. So what about categorical variables? So far we talked about these as continuous variables where 5 stars is better than 1 star. But what about when you have day of the month or words? How does logistic regression work with these types of variables? Remember, categorical variables are like labels, like zip code, or where having a greater value, there is no such thing as a greater value. Well, logistic regression does this by creating a feature per category. So if you have a categorical variable, say you have day of the month, so day can be 1, 2, 0 through 30, or 0 through 31, or I guess 0 through 30. You would have a feature or a column for each of those available days. And so does that make sense? What we're getting at then is if day equals 1, then that means the day 1 column would have a 1. And all the other day columns would have nothing. So there's a feature per category of your categorical variable. So this is why cutting down the number of words in the vocabulary of the review is important, because each of those becomes a feature in training our model. Go ahead. So this is what the model's learning as it's going through the data, as it's training, is it's minimizing the error on from the labeled column. So from whether the review is funny or not. And so this is what this is what the model's learned. So the way to think of this is, at the end of training, this is what the model has captured. It has captured weights for each of these variables. And so for categorical variables in logistic regression, the way to think of it is it's one feature per category of each categorical variable. Does this make sense? This is important for how we're dealing with reviews, which is why we wanted one-hot encoding. Because we said we only want the top 5,000 words, because each of those words is a categorical variable, and we're going to have a feature for each one.
So does it mean that it is independent for the, say, for day 1, independent of day 2?
Well, you can only be one of those days. Meaning the raw data set, say it was day of month, and it had values from 0 to 30. when you're creating one feature per category, there will be 30 columns, or 31 columns, and only one of them will have a 1. The rest will all be 0. Does that make sense? Another question. Yeah, go ahead.
Did you get rid of some, like, what was
Good question. Did I get rid of important words or what's common words, often called stop words in NLP? I didn't in this example, but you could easily do that. So you could drop the stop words. You could do some better tokenization of the strings. But for this example, as you'll see in a few minutes, it's okay. I didn't want us to spend a whole bunch of time just trying to clean the text. How much can you get, like how good is that first application, that first model, when we don't do a lot of sophisticated NLP stuff? You can always go back and do more. But that's a good example, that's a good idea. Dropping punctuation or expanding punctuation, so don't becomes do not, like that. Was there another question in the back? Go ahead. This is a raw count, unigrams. So this is just frequency count of each word. So we're not looking at bigrams or trigrams, though we certainly could. Go ahead.
So you randomly selected linear regression to start off. Is this the normal progression you start with linear regression and then move on to other models, or how do you actually define which is your first model?
Good question. So the question was, how do you choose the model? Why do we pick linear regression or logistic regression for this problem? It's a good question. I think I could probably spend a whole hour talking about that. But one of the simple things here is, what's our task? Is this a funny review or not? So the minute you're making a binary decision, you want a model that does that sort of classification, that does that sort of prediction. So that's why this seems natural to use. I want to predict 0 or 1, and that's what a logistic regression model helps me predict. So I'm using GraphLab Create for all the modeling, and here's why. A lot of machine learning packages require you to transform your data into a sparse matrix, or into thinking about it in matrix form so that the model can interpret it. And then you have to go back and remap to your raw data once the model's trained. And that's a nuisance. And it can get in the way, because you're maintaining this translation in your code that is just one more thing to maintain. So with GraphLab Create, we don't have to do that. We can take S-frames like the one we've been working on, and the models do sensible things with any of the data types. So you don't have to do this additional step. And the input can be sparse, dense. You don't have to think about matrices. You don't have to think about how the model itself is implemented in order to work with your data. And of course, everything's it's out of core, so you can work on data much larger than memory. And we, of course, think our system is robust. And we pick a solver for you. And for more complex models, that makes a lot of sense. That's an important consideration. What's the solver? You can select a solver, but we'll pick one for you based on the shape of your data. So this allows the optimization step to be one that you don't have to research up front. You can just get started, and then you can improve it, or look more carefully at which solver you'd like to use, but you don't have to pick one at the outset. Is there a question?
How do you start with determining the best solver? Do you use the shape of the data?
It's a good question. So the question was, how do you choose which solver? And it depends on the model. And so for each model, we sort of document the process for picking the solver. Does that help? Yeah, that's probably the simplest way to describe it. OK, so now let's get back to the notebook and actually do some modeling. And so we're at 11:50, and we only go to 12:10. So I'm going to speed up a little bit on this part. So guys, stop me if I'm going too fast. What we talked through training a logistic regression model, now let's actually train it. So a logistic classifier, meaning we want to classify. We're not going to use a validation set. Our data set's not that big. By default, GraphLab Create will take 5% of your data set and use it for validation. We're not going to use that. And we're going to take this encoded S-frame, this one that I just showed you a moment ago, that looks like this. This is what we're going to train on. and the target column is labeled funny. So that's what this funny, what the second parameter is. So let's run that. And somewhere between IPython Notebook and Jupyter, we lost the incremental output in IPython Notebook. So I only see output now when it's done. Even though we have progress statements, they just don't appear anymore. We have to figure out why. So let's see what we found. 147,000 examples. There's 2 classes. You're either funny or not. There's only 1 column with features. And there's exactly 5,000 features. Does this make sense? This is exactly what we did with one hot encoding, max categories of 5,000. We have exactly 5,000 features because logistic regression will create a feature for every category. In your categorical variable, we only have 1 categorical variable, which is the encoded feature. So we trained 10 iterations. Now let's look at what we got back as our trained model. It's a logistic classifier. Excuse me. A couple of the hyperparameters, L1 and L2 penalty for regularization. We have some sane defaults. We can just go with them. These are obviously things you can tune and make better. 5.7 seconds for us to train. And then you can see the most positive coefficient and most negative coefficient. And these are the encoded words. So we're done now. We've now got a model. Now let's set it up so it's easy for us to evaluate how well this model's doing. So that's what this function is. So this is, in a way, this is the whole pipeline. So now, given text, we want to return yes or no, whether it's funny. So what do? We take the text we're given, we create an S-frame out of it. We then call that select features function that we wrote earlier to get the bag of words representation. We then use the one-hot encoder that we fit earlier to transform that bag of words representation. In other words, only keep the top 5, only keep the words in the review that are in our top 5,000 words from our training set, and then use that transformed review to classify and call classify on the model. And then take those results and just add a column to make it easier to interpret that if you're class 0, then you're not funny. If you're class 1, then you're funny. So that's our little function. And let's run through some qualitative examples. So what do you guys think? Is this funny? Do you think this will be funny or not? It is not funny. But it's not super confident on that. It only has a 52% probability of not being funny. And what you'll find is for this very basic funny predictor, the probabilities are not great either way. I wouldn't deploy this to production. If you guys have a real application for predicting funny, I would do some more sophisticated stuff. But for today's tutorial, I think this is good. Are you sure this isn't the greatest review ever? Even this is not funny. Certainly seemed funny to me. Holy cow, amazing food and really cute servers. Funny or not?
Yes.
It is funny with 56% probability. And this is definitely not funny. Is definitely not funny. So, so qualitatively, what do you guys think? Is this a reasonable predictor? It's good enough? We should move on, do sentiment analysis. Go ahead, question. Yeah, that's a good question. I should be able to get back to that. I just, certainly we can. What I did in my set of S-frame operations is I nuked actually I could join my train table, which has the words, with my, actually, wait, maybe I can get back to the encoded. So I should be able to recover this. I just don't have it in my notebook. So that's a really good point. I should go back and see what are the most positive words. But I can give you the spoiler alert. It's curse words. So if you start cursing, you're going to have a funny review. And we'll get to that. So far we've done this logistic classifier for funny or not. Let's instead step back and think about overall sentiment. So far, let's talk about sentiment analysis. And we'll do this quickly, because I think, do you guys all have an intuition of what sentiment analysis is? We want the emotional or subjective meaning of text. Is this person's review positive about the restaurant or negative? That's the way to think of it. And this does require NLP. Unfortunately, for a lot of problems, there's no score. No one has voted that this person says this is a positive review or not. And this is why on Amazon you get hounded. Like, which review? Was it helpful? Was it not? Was it helpful? Was it not? It's so that you're labeling that data, so that Amazon can then better understand what the overall sentiment is of that product, which reviews to show you. The same thing Yelp is doing. You're often lacking this score. And so what do you do about that? I'm going to talk about that next. Modeling this is incredibly similar to what we've just done. We're going to use a bag of words representation, and we're going to train a logistic classifier. Again, where when you get to 1, that's absolute maximum positive sentiment, and when you're at 0, that's negative sentiment. So in between 0 and 1. But here's our challenge. There's no target. How do we develop a target? No one has told us whether this text is funny or not. We don't have anything labeled. One approach could be to cluster. We could try a different modeling technique. Let's cluster documents together and see which documents are similar. And if you want to find out more about clustering, come to Brian's talk later this afternoon. It's all about clustering and using density-based methods for clustering. Unfortunately, if we go down this approach, we don't actually analyze the sentiment. We've just found similar documents. That still doesn't help us with the actual labeling challenge of is this review and all of its similar reviews positive or not? So let's try a second solution. Can we use somebody else's data that's been labeled? Can we find an appropriate data source that is relevant, or not entirely relevant, but similar? And can we leverage that one instead? It's a pretty common technique. If I don't have labeled data, but you do, maybe I can use your data in conjunction with my problem, so I don't have to label the data. So this is what we're going to do. With sentiment analysis, with GraphLab Create, we offer a pre-trained sentiment analysis model. You can always train using your own label if you have labeled data. Otherwise, we have a pre-trained model that's been trained using 20% of random Amazon review data. And the Amazon review data has a score. And version 5 of the Yelp dataset using stars, the number of stars, as the target. We binarize these features. So greater than 3 became 1, less than 3 became 0, and 3, like you're absolutely neutral in your review or your score, we discarded. And from our observation using validation sets, we got 88 to 90% accuracy. But there's more details I should cover about this. And we have obvious limitations here. Only English. And this works best if your documents are roughly the same size. Question?
So, how do you get the Amazon data?
Oh yeah, so good question. How do we get the Amazon data? 2 ways. One, Stanford published from 1996 to 2013. It's a SNAP data set from the SNAP group. And then it's been updated by a researcher at UCSD. I think his name is Julian Macaulay. And that takes you through 2014. So this data set is publicly available. I wish I could say we had some secret sauce to get it, but we didn't. And we document where we got it from, and anybody else can get it too. So, and then a more advanced technique of sentiment analysis is often called aspect mining. I don't really like that name. It seems like a weird name to me. But the intent here is to, I don't care about the whole review. I don't want overall sentiment. I want sentiment about part of the review, the part that talks about something I care about. So I showed you in the demo burrito and authentic. So I care about authentic and burrito. I only want to see the parts of the review that talk about those things, and I want to predict the sentiment about those things in the review. So that's so this is more advanced. Again, you can train your own model, or you can use the pre-trained model. And typically for aspect mining, you want to split your document into sentences. But not always. Maybe if you're looking at tweets, you actually want the whole tweet. But for the example we'll work through, we'll split the reviews into sentences because that's more important. Go ahead.
The natural language fits in. Do you use any of those things?
Of course. So natural language, there's lots of ways. So the tokenization of the string. In order to do aspect mining, you need to tokenize the string, create a reverse index. That tokenization leverages natural language, right? So we're using the NLTK punct tokenizer. You could also use, there's a bunch of different tokenizers, but this leverages the grammar of the language, which is why it only works for English. And so, so I've got this in the notebook. I'm thinking in the interest of time, I'll plow ahead and finish the slides in the next 5 minutes where we cover deployment, and then we can spend the last bit of time actually working through both sentiment analysis and deployment in one shot instead of switching back and forth. So far we've talked about modeling. So let's finally talk about deployment. So I'm going to give a really quick overview, and I encourage you to come to Sean's talk tomorrow. He's going to go through a lot more depth. But what's your goal when you're thinking about production? You're thinking about integrating this model that you've trained with the rest of your application. You want to be able to update the model with new data. So say you're training nightly or hourly. You want to make that update process seamless. And then, of course, you want to make the improvement or increment, the next version of the model. You want to make that deployment seamless and easy as well. You want to make sure you can use this system for real-time predictions, meaning it's got to have low latency. And you want to be able to use the same system for online experimentation, A/B testing, multi-arm bandits, so that your system becomes adaptive. So with Dato Predictive Services, we have a product that gives you all of these things, and that's what we'll go through in the notebook. So I don't need to cover all the details here, but it makes doing the steps for deploying a model as a service really straightforward and easy. Okay, so that's it for deployment. And that's it in terms of content, but let's get through the notebook. So training the sentiment analysis, the very first thing is we have labeled data, right? We know whether something's funny or not. So I don't have to do my bag of words anymore. I don't have to do my, I don't have to do bag of words anymore. I can instead just train this directly. And it took a little bit longer because it didn't do the, I didn't use the one-hot encoding, but I'm still done. And you can see that I've gotten, the way this model was trained was a bag of words plus a logistic classifier. So now I can predict on this model given some text. So I wrote, the chicken was bland and unfortunately undercooked. The server was prompt, but the food was not served hot. This is not funny. Now, how about this one? Holy cow, the server spit in my face, but damn, that was a tasty burrito. That's pretty funny. And so we can always calculate the overall accuracy by evaluating against the entire data set. And of course, on a larger data set, a real problem, you'd want to hold out some data and use that for evaluation. But here we are at 94% accurate from our entire data, from our data set. Okay. So the pre-trained model, let's use that one instead and see how well we do. So I'm going to load my data again, but I don't have to do all the same steps, my raw data. So you see that I just have this text column. That's the only thing I have now. And I'll call sentiment analysis. If you don't specify a target, we're going to use the pre-trained model because we don't have a label. So we're done. By the way, I should have mentioned all this stuff's happening on my laptop, so there's no magic server sitting somewhere. So you can see this time this model looked at all the data. It didn't take things that only had votes, had some votes or not. It was all 230,000 rows. Again, bag of words with a logistic regression. How did we do for overall sentiment? Because now we're not trying to predict funny because we don't have that label anymore. We're now trying to predict overall sentiment about the review. So it turns out my chicken was bland is not a positive sentiment. That sounds right. But my holy cow, the server spit in my face, but damn, that was a tasty burrito. That is a positive sentiment, but it's not as high as using the sentiment analysis classifier with the funny label. So if I was trying to predict funny, that's better than if I'm just trying to predict overall sentiment, whether it's positive or negative about the sentiment of the review about the restaurant. And finally, aspect mining. This takes a couple minutes. This will take a minute to train because it's creating a reverse index. First it parses and then creates a reverse index. So we're splitting by sentence. We're again using just the raw text in the reviews. And so for this example, I care about the most positive sentences that talk about teriyaki and rice in the restaurant review. Last night I wanted teriyaki, so this is what I thought about when I was working on the notebook. And then also the most negative. And finally, we can get an overall summary. And when I ran this last night, it took about 1 minute and 8 seconds to train the model. So we'll let that keep going. And I won't get time to cover the deployment stuff, but you can see exactly what you need to do. So if you want to do this on your laptop, you set up AWS credentials, tell us where and how many instances you want to launch in your deployment of predictive services, one command to launch the cluster. And all this runs in your account. We don't have access to your data or anything like that. And when you set your AWS credentials, they don't go anywhere. We're just setting environment variables on your machine. You're making all the commands to EC2 directly from your laptop. So you can see we easily can add this funny predictor function that we used before as a service and give it an endpoint. That becomes the REST API. And then we can apply changes and now query this using a built-in Python library, or you could just as easily query from it's just a REST API, so you could query from any client. And what I deployed here was the funny predictor. So not any of the newer sentiment analysis models we just trained, but the very first thing we did, which was predicting whether something was funny or not. And so that's it. Let's see if my model's done training. I'm happy to take questions, and I'm certainly here for the rest of the conference. You can do all the assignments using other tools as well, but you can also use Dato, which you can get an academic license for and is free. So this is a great way to get deeper. This is a case study-based approach to machine learning. So you don't start with proofs, you start with applications, and then then the math gets introduced slowly. So it's a much more natural way or more applied way, and the feedback we've gotten has been really positive. And of course, finally, come to Brian's talk this afternoon. He's a better speaker than I am. And it comes to Sean's talk tomorrow. And of course, you can reach out to me. I've got my email address on the slide, and I'd love to hear from you. Come to our table out in the hallway if you want to find out more about Dato. Thanks so much for your attention, guys, and thanks for the questions.
Thank you.